Today we're going to look at the Atwood's machine problem. To start, we have a pulley that is frictionless upon turning, but there's enough friction to hold the string tight against it. First thing I want to do is I want to draw a force diagram for each of the weights. The first one we have is the green one. Call this M1, and when I go to draw the force on M1, we have the force of the earth down on it, which we call M1G. And we also have the force of the string in the up direction, which we're going to call T for tension. In looking at this problem, it's obvious that the heavy weight is going to accelerate down and the lighter of the two weights is going to accelerate up. Therefore, when I look at the force diagram for the lighter of the two, the tension should be greater than the M1G because the net unbalanced force has to be up because the acceleration is up. Drawing the force diagram for the blue, the heavy weight, we know the earth pulls it down. With M2G. The string still pulls it up, still the tension. And what we'll notice is that because it's one piece of tight string, the tension value is the same for both. So immediately in the beginning, we get a sense that the tension has to be greater than M1G, but has to be less than M2G. The next thing to do is solve for the acceleration of the system. When I go to solve for the acceleration of the system, we know it's equal to the net unbalanced force of the system over the mass of the system. To go from there, the net unbalanced force of the system is the difference in the weights. If we consider this whole thing the system, the tensions are equal in strength and opposite in direction, act in one is up, the other is up, but because they rotate over the pulley, they cancel each other out. Therefore, the net unbalanced force is M2G minus M1G. And then over the mass of the system, which is M2 plus M1. From there, we can plug and chug, and we can solve for the acceleration of the system. The next thing we want to do is solve for the tension in the string. In order to solve for the tension in the string, we need to isolate one of the two masses. So let's do the green one first. When I go to calculate the acceleration of mass 1, it's going to be equal to the net unbalanced force on mass 1 over the mass of mass 1. In this case, that means the acceleration of 1 is equal to T minus M1G all over M1. And the thing I like about this is that the acceleration of the system is equal to the acceleration of mass 1. So once you plug and chug and solve for this, then we can get this value right here, and you can solve for tension. But because it's nice to make sure that you did it right, we can also use the same strategy to solve for the tension in the string using mass 2. It's exactly the same, only different. The acceleration of 2 is equal to the net unbalanced force on mass 2 over the mass of mass 2. And in this case, the acceleration of 2 is equal to, and it's going to be different. We always do, to keep a positive acceleration value, big minus small. So this time it's going to be M2G minus T all over M2. And when you solve for that, plug and chug, solve for the tensions, and they should match.